Okay, let's go ahead and get started. We're going to be talking about Earth's natural resources today. Well, give this a chance to warm up. And then the rock cycle on Thursday. We're taking our rock walk this week, so hopefully everybody coming to lab today is wearing comfortable shoes so that we can take our walk. Next week's the climate summit. I'll be making assignments for that in lab as well, so that'll be happening. I'm going to try to tie together everything that we were talking about last time and sort of take another look at, again, what are typically called environmental and economic geology today, and then we'll look at the rock cycle specifically on Thursday. And the rock walk is going to walk us through the rock cycle as well, so we'll hit on a number of the same topics in each of these areas. I opened last time with the questions of, what would, if you can put yourself into the shoes of a culture prior to science, and you were looking at natural wonders and natural disasters, how would you explain those things? And that gets us into, a way of thinking about discovering the Earth and discovering things about the Earth. If we think back to that same process, we remember perhaps going from the Stone Age to the Bronze Age to the Iron Age, and then from the Iron Age to modern technology. I mean, we have discovered things about the Earth over time that have allowed us to use the Earth's resources for our own uses. So we're going to talk today about what those resources are on the Earth, natural resources, but we're also going to then talk about how we have used these things and how we may need to plan for using these things into the future. We have typically used these things thinking they were inexhaustible. I mean, the Earth is very large, and it seems like there's always going to be plenty of whatever it is we need. And there really is plenty, but how we use it has led to some other issues. So we'll talk about ores and minerals. These are the metal ores. We'll talk about hydrocarbons. We'll also talk about timber, air, and water. Again, there's a lot to talk about in here, a lot of different areas we can go, and eventually we're going to get to biodiversity. Now, biodiversity we'll talk a little bit about today, but we'll come back to that at a later time too. We'll also spend more time on air and water when we talk about weather and climate. So we'll try to focus a little bit more on resources here. See these prospectors looking for gold, and now the question is, can you find any of these other rare earth metals? These are actually more valuable to us right now. These rare earth metals that are used in cell phones and other things. Anyway, so that makes that kind of funny, because at the time he never would have thought about the value of these things, and I'm not going to try to go through them for those necessarily. And the other thing that we have to get on today, oil shales. The Chronicle this morning has an article, where is the next big oil shale find? We have the Bakken Shale and what's the one here in Texas that's been very productive lately. Sort of a new technology has allowed us to utilize new resources. Again, wouldn't have been available to, or wasn't available to us. We knew it was there, but it wasn't cost effective to go get. So we'll talk about fracking and all kinds of other types of issues as we go forward. Again, these are just to sort of frame what we're talking about. Tree huggers versus people who want to develop the forest, that kind of thing. We're going to be talking about some of these debates, some of these issues, and thinking about where you might fall on these things. I wish I would show the whole thing here. This is one of the cartoons I've used a lot. The paper mill is producing a lot of waste. The water treatment plant is cleaning it up. Same company. Is that a conflict of interest or not? So there's all kinds of things going on in today's world that, as I've always emphasized, you have to help make these decisions about how we're going to deal with these things. This one's sort of interesting. I don't know where, if you followed that controversy with the teenager who was hunting big game in Africa and putting it on Facebook, and some people were outraged and some people supported her right to do that and so on. So again, these are issues that have different sides to them. All of them have different sides. There is science behind all of these things, but science won't make these decisions for us. We can use the science as tools to help make these decisions for yourselves, but it's your responsibility to make these decisions and to participate in the discussion about how to use natural resources or how to protect natural resources, how to sustainably use natural resources. What are you willing to do without? What are you not willing to give up? These kinds of questions are going to play a big role in how we go forward. So, a lot of the things that, when we talk about sustainability, different issues that I want to frame this through, we do have a natural environment that we still realize provides resources. We can utilize those resources, but we may have to protect the environment enough to keep these resources available. And if you consider two of these resources being clean air and clean water, that presents most of the conflicts that we see with some of these other forces. So again, how much are you willing to pay for a product if a company has to start controlling its emissions more and the price of the product goes up? Are you willing to pay a little bit extra to protect air and water? Those kinds of questions are things that you need to think about. We also have a man-made environment. Interestingly enough, our man-made environment, which is cities and so forth, also has an urban ecology. Urban agriculture is a really big deal right now. A lot of communities, including Houston, are encouraging more urban agriculture, growing your own food on your rooftop or in a garden, even in a small garden, rather than putting pressure on the mechanisms that provide food that we're used to. I will bring up just for the fun of it, we're only about half here, but this idea of a green economy is an interesting one. There have been, again, a lot of, and this is typical of anything really. I mean, we are perhaps a little bit more polarized in our society than we used to be, but not as much as it seems. There's always been a polarization in ideas, and so some people see the green economy as a great opportunity to start new industry, to invest, and have that investment pay off in a new round of economic boon. If you think about in the last few decades, we've had the communications boom, the internet, and it has spawned just whole new industries, right, that didn't exist before, simply because of the internet. Prior to that, NASA and the technology that was spun off of NASA. Prior to that, the atomic bomb, the science that went into developing that spun off a large number of industries. And so people have looked at those models and said the government should invest in the green economy just like it did in the nuclear race, finding the atomic bomb first. Even though the motivation for that wasn't initially economics, it led to a huge economic opportunity. Same thing with NASA. It wasn't initially intended for the economic benefits, but it did spin off all of those benefits. So some people say we should invest in a green economy in the same way because it will spin off a lot of new opportunities. Other people say that's just a boondoggle, it's a waste of taxpayer money. We need to let free enterprise do it. Free enterprise, that model is what spun the computer revolution, right? People messing around in their garages trying to come up with a better computer. And so it wasn't government investment, it was just a lot of innovators working on problems on their own and coming up with solutions. And so some people argue that that's the best method to pursue a green economy, and others say a government investment. So that's up to you, right? You have to decide these things. How are we going to go about this? So on and on and on. I want to show you, again, just for the fun of it, but it's not always easy being green.
It's not that easy being green. I will spend each day the color of the leaves. When I think it could be nicer being red, yellow, or gold, or something much more colorful like that. It's not that easy being green. It seems to blend in with so many other ordinary things. And people tend to pass you over because you're not standing out like flashy sparkles in the water or stars in the sky. But green's the color of spring, and green can be cool and friendly like, and green can be big like an ocean, or important like a mountain, or tall like a tree. Well, green is all there is to be. It could make you wonder why. But why wonder? Why wonder? I'm green, and it'll do fine. It's beautiful, and I think it's what I want to be.
All right, I always show that for the fun of it, because I grew up with that, and it's worth pointing out, of course, that was not written initially for thinking about the green economy. It was written for a much more important social issue, but I think it's sort of funny in retrospect now to bring it up. It's not easy being green. And if we are going to try to live this way, we have to make some tough choices. And I'm not saying, again, you're going to have to decide for yourself whether or not you agree with a carbon tax, whether or not you agree, again, to pay more for certain products, whether you agree to pay more for LED bulbs and replace all the light bulbs in your house because it's more energy efficient. How much is it worth it to you if you build a house in the future to have solar panels built into it? Are you willing to pay extra for that? It may pay off in the long run, but how long will it take? Is it worth the investment? All kinds of decisions are going to be yours to make as we go forward. All right. Just real quickly, if you look at the Earth, we're looking at basically here a number of things can be taken from this, but it's sort of the temperature map of the world. But the colors are not what you would expect. The red is not hot, that kind of thing. But it's also a rainfall map. Where's production in the world? Where are things coming from? We can think about a lot of these different geopolitical arguments. Where is most of the world's population? Paul Krugman, the economist who wrote "The Earth is Flat." The whole point of that book is that we are now so connected, not only by the internet, but also by shipping and air freight and all these other things. Fairly recently, it's been cheaper for companies to hire people in India to do jobs that normally would have been done here because the internet allows them to be connected instantly to whoever, where the needs are. So India and China and those emerging economies, they're very powerful economies. They're growing. They'll exceed ours fairly within the next, decade or two. So what is that going to mean for innovation, for us to, as a country, to remain competitive, to remain the lone superpower? Will that continue? As we go forward, not too far into the future, we're going to have to consider a lot of global issues. We can't just think too locally. If we think about Texas, of course, we can start thinking, we have our own issues. We have drought issues, we have, other types of things going on, but globally, not only with competition, but water resources. There's only so much clean, fresh water. What are the demands on that water? And is that going to increase, those demands? A lot of issues to consider there. Again, your own decisions actually can have a big role to play in this. I always relate it to my wife's an attorney, and she was really into the constitutional law, and voting is very important to her. And so whenever she questions me, why are you recycle every bottle? I mean, it's okay to throw one away. I said, well, it's like a vote. One bottle by itself may not mean a lot, but when everybody recycles, it does mean a lot. It adds up. So any decisions that you make along these lines are similar to that. One light bulb at a time. Each light bulb is not particularly important, but if everyone changes to more efficient light bulbs, it will be. So you're going to have a lot of decisions to make, and where you think you want to make those decisions is up to you. We'll get back to, we'll show something about the plastic bottles and recycling and things like that as we go forward, but I just think these are interesting, worth looking at. So let's look at what some of the environmental concerns are. What are some of the concerns right now? Obviously pollution, I've mentioned air quality, water quality. We've got nuclear waste that we have to deal with. We'll talk a lot more about climate change. Next week's lab is all about that. And then habitat and biodiversity, as I mentioned, we'll talk more about that as well. And why is it important? Why is it important to care about biodiversity? So we'll come back and talk more about that. But let's start with Earth's waters. Where is Earth's water? Most of Earth's water is in oceans, right? 70% of it. It's salty. We can't drink it. If you drink it, you'll die because it'll upset, the balance of electrolytes in your cells, and you won't survive. It's the rhyme of the ancient mariner, right? Water, water everywhere, but not a drop to drink. You can't drink the oceans. Now, we can desalinate the oceans, but that's expensive. That may be something that we have to look into doing more of, though, now, as well as in the future. There are parts of Texas that are looking at desalination to provide their water resources because their traditional resources are running dry, primarily groundwater. Groundwater is the second largest reservoir here of water, and it is fresh water. So we can drill into the ground, drill wells and bring that water up to the surface and drink that water. We also have rivers and streams and lakes that collect fresh water. We might have to clean it up a little bit, but you don't want to drink water directly from Lake Houston, probably. You're going to go on Lake Houston fishing and then just dip a glass of water and drink it, right? But that's the water you drink every time you open the tap or cook with. It's been cleaned up, and we'll talk a little bit about those processes here as well. But the point being, as we go through this, that the amount of fresh water we actually have for drinking is actually very small. The percentage of the Earth's water that is available is only about 4%. About 4% of the Earth's water is actually available to us to drink. Now, if we go grab an iceberg and melt it off the coast of California, we increase that percentage a little bit. A lot of that's in ice. But again, it's not accessible. It's not something that's easy to get to. We're used to water being cheap. That may not remain the case as global demands for water increase and the availability of water becomes more of a political issue, where some countries have plenty, some countries don't have enough, some regions of a country have plenty, some regions don't have enough. There's already a lot of water conflicts going on between California and Arizona, for instance. Have been for a long time, because California diverts a lot of the water from Arizona into their own reservoirs. So it's been going on, but it's only going to get worse. The water cycle is pretty straightforward, and y'all are seen this a lot. I do like to point out a couple things that are worth mentioning, in addition to the normal, what you think of the evaporation of water, the condensation of that water into clouds, and then the precipitation of that water back down to the surface. Wherever that water falls is important. If it falls on a high area, it's going to run downhill. Water always flows downhill, so it's going to create rivers and streams. It's going to collect in lakes and seas, as well as water falling into the ocean. All of these rivers and streams are eventually going to end up into the ocean. There's also erosion going on. They're carrying sediment with them into the ocean. Some of that water is soaking into the ground and recharging groundwater. How fast the groundwater resources can be recharged is an important issue. If you live in Austin, for instance, where all of your water comes from groundwater, it's an important issue. Is there enough rainfall to recharge the groundwater, the aquifer? It's also more of a, if you pollute. If you throw your cigarette butts out the window in Austin, it's a much bigger fine than if you do that here in Houston. Here in Houston, you might have somebody, write to "Don't mess with Texas," and you get a little letter in the mail, but you're not likely to be fined. You get caught doing that in Austin, you are going to get fined because those chemicals are going to end up in the groundwater. If you throw something out on the ground, it's going to leach into the groundwater, and that's your drinking supply. And if it gets polluted, it costs money to clean it up. Right? We all pay money to clean our water, to make it ready to drink, but we don't pay the true value of water at this point because we're all subsidizing it with our taxes. It's interesting, right? If you calculate how much you're paying for a bottle of water by the gallon, you pay a lot more for a bottle of water than you pay for gasoline, right? But you don't drink a gallon of water at a time. So you think, oh, okay, yeah, $1 something for 12 ounces. I'm willing to do that. Then you go fill up your tank and you think, oh my goodness, $3.50 for a gallon of gas? But you use a gallon of gas pretty quickly, particularly in Houston. So the value of things, it's an interesting argument. It's going to come up a lot in our discussions, even though, again, the science doesn't have anything to do with the economics of these things. Science can tell us, for instance, ways of putting value on things. I want to, again, we sort of, in the last presentation, I said I didn't get all the way to the sedimentary processes, surface processes. I said I would get back to that. And this slide gives me a chance to mention these things again. There are a lot of features in our landscape that are created by the flow of water and ice and wind blowing across the surface. And mostly water, flowing water does most of this work. If we lived in the Midwest, though, I would talk a lot more about glaciers and the landscape that has been created by glaciers moving over the land and then retreating. If you've been to Minnesota and the land of 10,000 lakes, those lakes are kettle lakes left behind by glacier, the erosion of a glacier, and it melted and filled the lakes up. We live in a coastal area where we have deltas, we have rivers bringing stuff to the coast. Our entire region is basically one delta laid on top of another over time. Anyone from Louisiana, 7 lobes of the Mississippi River have created the current coastline of Louisiana. Similarly, in Texas, most of our sediments all the way down to Corpus Christi have come from the Mississippi River, brought down and then distributed along the coastline by longshore current and other forces. So it's mostly sediment. We have sediment, very deep sediment under our feet. Again, you go to Austin, you've driven up onto the Edwards Plateau, and you're on rock, solid rock. Not so much sediment. And erosion has removed a lot of that sediment and left behind a lot of other features. It makes a difference whether you're in an arid region or a humid region, what features you see. Even along the coastline, what types of systems you get. Our barrier islands are sand and silt and clay that has been built into islands by wave energy and the longshore current. You go south of Corpus Christi and it's mostly carbonate sands, white sands, that are from the evaporation of water and the condensation of calcium carbonate from solution. It's a more arid region, we're a more humid region. Not just where you are, but where the sediments are coming from. Wind can form dunes and a number of other things. If anyone's been to White Sands, New Mexico, those dunes are gypsum from lakes that have dried out, playa lakes, ephemeral lakes. So they dry out, the gypsum gets blown away, piled up into dunes. It's white sands, but it's not the same white sand as you'd get in Florida. You can crush the white sands at White Sands, New Mexico, between your fingernails. It's softer than your fingernails. You can't do that in Florida because it's calcite. It's a different mineral. We'll talk a little bit more about minerals in a minute. If we follow the Trinity River and the valley that it has cut into the ground as it's flowed through this area, it actually has cut a valley all the way out to the edge of the continental shelf, because 10,000 years ago, that's where our coastline would have been, about 200 miles farther out to sea on the edge of the shelf. And we would have seen these canyons, not underwater, but actually on the surface. The oceans have risen over the last 10,000 years to cover that up. And that process, again, has reworked the coastline over and over again. So we've got barrier islands forming and then being destroyed and forming again and being destroyed and over again. It's a natural process. Barrier islands naturally are eroded away. They're ephemeral. But we've accelerated that process by trapping the Mississippi River in its current path. It now takes all of its sediment off of the continental shelf into deep water. None of that sediment gets carried by the longshore current to replenish the islands, not only in Louisiana, but all the way down to Corpus Christi. What's that? No? Okay. So, now the only forces working on our islands are the erosion forces. There's no new sediment coming in. So there's a lot of things that we can talk about here, a lot of different types of estuaries that can form behind these barrier islands. We have bays here, basically the river mouth flooded, and that's our bay. We have Laguna Madre south of here, which is a lagoon. And so a lot of different features. And again, I don't have time yet, really a chance to go into a lot of that. But it is worth talking a little bit more about the Mississippi River. This is what's called the watershed of the Mississippi River. A watershed is the region in which all of the water that falls will eventually end up in that river. So look how extensive this is. From the Great Divide to the Appalachian Mountains, all the rain that falls ends up in the Mississippi. Now you can see we're not in that particular delta. Our rivers start like in Texas. I mean, the Trinity River starts just north of Dallas. It's not a very massive river compared to the Mississippi. So obviously the Mississippi River has had the most dramatic impact on the coastline of the United States. And really, again, the Mississippi Delta is all that sediment on top that's filled in what would have been ocean prior to this current river's flow. But it's also moved around a lot. Let me see, I guess I don't have, let me go back. Again, the Mississippi River currently is flowing out the Birdfoot Delta. It's currently flowing this way. It's gone all the way out past the continental shelf. And if you go out in where the water gets deep or shallow, and then it drops off very suddenly. So the sediment is now being dropped off that continental slope. A couple things worth mentioning there. All the organic material that's being brought is now ending up down there. It's creating an anoxic patch where there's no oxygen in the water because all the organic material gets broken down quickly and uses up all the oxygen. That's causing a problem with a lot of industries. It normally would flip back and forth, and if we'd let it, it would move back into the Atchafalaya Basin. But we have dams and all levees and all kinds of things to keep it going the way it is because we have ports in New Orleans and Baton Rouge. Same thing here, or all the way up. It's not just New Orleans and Baton Rouge. Keep going. You've got Memphis, St. Louis. These are major ports for, again, industry. So if the Mississippi River moves, guess what? No business on the Mississippi River. It would be devastating. So we have to deal with the problems that are generated by keeping the Mississippi River in its current path. And that is coastal erosion and saltwater intrusion and the impacts on fisheries and local businesses and those kinds of things. And so we've sort of chosen to spend billions of dollars rebuilding the coastline rather than give up our access to these ports. It's the correct economic decision, right? Spend even $2 billion rebuilding the coastline, or give up the $1 trillion of business that's conducted across these various ports along the river. So again, but those decisions and whether that money is worth spending or not is up to voters. It's up to you guys. Well, I mentioned, groundwater, how important that is. Even here, we used to rely more on our groundwater than we do now. We don't rely as much on groundwater in Houston as we used to, but if you live in Montgomery County or farther north, you probably do still get most of your water from groundwater. But the reason we stopped doing that in Houston is because when you take the water out from under the ground, our ground is not solid, so it sinks. It settles. It's called subsidence, and we have a lot of issues in Houston because of subsidence. It undermines foundations of buildings. There's a subdivision in, I guess it's in, it's not in Daytown, Pasadena somewhere, that's been flooded. They built the subdivision. No one ever lived in it because by the time it was finished, it had sunk too much, and the water floods in, and you can't live there. So subsidence has been a real problem, so we've stopped using groundwater in Houston. Now we use surface water, reservoirs, and we treat that water. There's two sides to water treatment, okay? There's taking water from a reservoir and treating it so that it's safe to drink, and then there's treating the water that we let go down a drain enough so that when it gets out into the environment, it's not going to cause too much trouble. There's a lot less treatment of that water than there is of the water that we, again, drink. And so it's worth thinking about what you let go down a drain. We have the EPA coming soon, and we have to make reports in our labs. Everything we put down the drain, we have to keep track of, and we have to report. This is what we're putting down the drains. There are some things you're not supposed to put down a drain. You're supposed to put it into a different type of container and put it in a landfill. We'll talk about landfills in a minute. So how we dispose of our waste, again, we used to think the earth was just so vast. Oh, there's plenty of room. Throw the waste out there. Just throw it out where you can't see it. Throw it in the ocean. Throw it, behind this hill or whatever. Well, we learned pretty quickly, it doesn't stay out of sight very long. Wind and rain and stuff tends to move it around. It's not only unsightly, it's unhealthy. When we learned about, oh, bacteria and viruses, all this waste is a really good breeding ground for all these really dangerous pathogens. We'd better keep our waste away from our food supply. Matter of fact, let's bury it. Let's put it in the ground. Well, then it leaches out into our rivers and streams, and we realized, oh my goodness, it's still getting into our water and we're getting sick. So we've, over time, learned more and more, and now we're learning too just how much damage we've done to the oceans by continually dumping material into it. But it costs money to manage this waste. And so everybody, again, has to sort of decide what you're willing to do. All right, this is just another picture, again, of where the water is. And we can work this down. You can see most of the oceans most of the Earth's water is in the oceans. Very little bit of that fresh being in glaciers or icebergs. Groundwater and glaciers hold the next largest amount. And then finally, rivers and streams and swamps and whatever other surface freshwater area there is. And then here's a landfill. Houston actually has a very good landfill. It's a model landfill. If you haven't visited, it's worth a visit because it's really sort of interesting. It's also the highest. You can look out the window when we get to lab. You can look out and see it. It's like this mountain off in the distance. It's our highest feature in Houston because basically we truck all our trash in there and then we bury it. And every day it has to be buried. It's capped every night by clay that's put on top. It's lined around the bottom to keep things from leaching out. And it's managed very carefully. It's actually pretty good. If you do it correctly, it now actually generates gas, methane gas, that can be siphoned off and sold and used. Matter of fact, they do that to generate electricity. So it's a whole process. Water purification is another issue. Again, there's different levels of purification depending on what it is you have to clean up. If you just have to get silt and sediment out, you can just filter it. If you have to get rid of bacteria or something else like that, you can chlorinate it or fluoridate it and kill those organisms. And then you can get the chlorine back out. Obviously, you don't want to drink chlorinated water, but that'll kill everything. But if you've got something like PCBs or dioxin or some other dangerous chemical, those are very difficult to get out of the water. I mean, it's very expensive because it can't be done just by filtering or by treating the water with a chemical. It has to be, again, it's a very expensive process. So we have to monitor those things very closely so that we don't have to, hopefully, spend more money to clean something up than it would have cost to just manage it in the first place. There are a lot of Superfund sites in Houston, areas where companies, before we knew better, were dumping a lot of very toxic wastes. It was leaching into the water supply. So when we realized what was going on, the Clean Water Act now requires that these companies clean that up. And if they're found to have deposited things in there illegally, taxpayers pay for that cleanup initially, and then we sue those companies for triple damages to pay us back. But it's better to take care of the problem before it becomes a problem than after. It's a lot cheaper for us as consumers to say, hey, you need to make sure your toxic waste don't go into the environment. We're willing to pay more for our products. It's cheaper to do that than it is to come back later and pay taxes to clean up these Superfund sites. So those kinds of things are issues, again, that a lot of times people aren't aware of and perhaps should be. All right. Again, I'm not going to go, just for the sake of time, into all of this one anymore. It's just a bigger picture of that. I want to get away from, a little bit away from, I guess what might be, not depressing, but I'm putting a lot on you, right? A lot of responsibilities, a lot of things to think about. I remember I was teaching 7th grade one time, and we talked about acid rain and the ozone hole and climate change and pollution and all these things. And at one point the student was like, doesn't anything good ever happen? And it sort of woke me up a little bit. It's woken me up to a perspective where, our entire history of technology has been a lesson in creating a problem, fixing it, which creates a new problem, we fix that. And so there's always problems, but we've always, up to this point anyway, found solutions. The solutions, however, come from the public paying attention and making those solutions important and providing the impetus for fixing them. We have plenty of problems today, and whether we fix them or how well we fix them is, again, in a large part up to society to decide what our priorities are and what we're willing to pay. The ozone hole is not as much of a problem as it used to be. It's still there, but it's getting smaller because we stopped putting chlorofluorocarbons in our spray cans. We sort of decided that as a society, that let's do that because we don't want to all get cancer because there's no ozone in the air anymore. All right? I'm willing to pay a little bit more for my spray paint or my aerosol deodorant if it's going to help save me from cancer, right? That decision was it wasn't made quite that simply, but that's sort of the decision that was made. So those kinds of things are going on. But let's talk a little bit more about Earth's waters and the environment. Just from a descriptive standpoint, talk about the oceans. We talk about oceans, we can look at it in 4 different ways. Chemical oceanography, physical, geological, and biological. And geological we'll spend less time on, but I've been talking about a lot of things in there that I want to clarify. This is what the ocean composition looks like, other than the water. This is the solid component or dissolved component. It's mostly sodium chloride, which is table salt, so when you dissolve salt water. But when you get sea salt, you also have a number of other salts in there. Potassium chloride, calcium chloride, bicarbonate, magnesium chloride, and so forth, and some other things. That's why sea salt's a little different than table salt. Table salt is just purified sodium chloride. So that's sort of chemical oceanography. That's what's in there. Where did this all come from? It came from rocks. Water falling on rocks, dissolving the rocks into solution, carrying that material to the ocean. That's where all the salt in the ocean has come from. It's come from rocks. So we'll look at that when we talk about the rock cycle. It's also worth noting that the pH of the oceans is balanced. It's buffered. What we mean by that, if you remember your chemistry from high school, what a buffered solution is that it can handle the input of an acid and keep its pH stable. Or a base. You can add a base to it and it will react in such a way to keep its pH stable. The ocean has a buffer system. It's bicarbonates that can absorb and release hydrogen ions to keep the pH stable. Your blood has the same buffering system, the exact same system. In many ways, your blood also has the almost exact same dissolved mineral content. Those are what we call electrolytes. So when you drink a Gatorade or something, you're trying to get that potassium and the sodium and all those electrolytes back into your blood. So the composition of your blood, the buffering system, is almost exactly the same as ocean water, which is an interesting comparison, which again we may come back to at some point. When we talk about physical oceanography, we're talking about tides and waves and currents. And I'm going to focus more on currents because it's going to tie into climate when we get to this next week. And primarily the major surface currents. Now these are driven by the formation of cold, salty water at the poles. It's called Antarctic bottom water and Arctic bottom water. As water freezes, it leaves behind the salt behind, and so the water becomes more concentrated with salt. And it's cold, so it's dense. It sinks. It sinks down and then flows towards the equator. That's at depth. It then rises and flows back towards the poles on the surface. Now, because the Earth is spinning, that return current gets bent into a curved line instead of a straight line. And we get what are called the gyres, the ocean gyres. If we look at our own gyre, the North Atlantic gyre, we can see the Gulf Stream coming from near the equator up to our coastline, around, and then back towards Europe. Some of it breaks off into the straits, the Labrador Strait there. This interest, again, whether this current is strengthening or breaking down is an important question in climate change. But a lot of the water then comes back. If you've ever been swimming in Southern California, The water's cold, right? Go to San Diego, step in the ocean, and go, whoa, why is the water so cold here? It's a beautiful warm day. Well, because it's the gyre coming from the north. It's carrying cold water down. The same latitude in the Atlantic is warm water. And that's because it's the gyre coming from the equator. So these gyres do move the ocean's waters around quite a bit. This is why hurricanes that form in the Atlantic end up coming towards us, whereas storms forming in the Pacific end up mostly in the Indonesia area, in that area over there. So there are a lot of storms, a lot of hurricanes are called cyclones in other parts of the world, northern and southern hemisphere. Geological oceanography looks at the shape of the Earth's of the ocean's floor. This is a map with the water taken away, and you can see there's a lot of interesting features on the ocean floor. There's these mid-ocean ridges. Remember we talked about those, these mountain chains. There's deep valleys, the trenches, and so forth. But also, where did I thought I had this one. We talked about passive and active margins. And I've been talking about this a lot. I've been using the term continental shelf. If you walk out into the Gulf of Mexico, the water gets deeper fairly gradually, and then eventually it drops off very suddenly. This is not to scale, but to actually put this in a diagram and have all these features, you have to really compress it. But you have a very broad shelf, and then a steep slope, and then it bottoms out into what's called an abyssal plain. So the ocean itself has surface waters where sunlight and oxygen dissolves into or shines into to a certain depth. That light can only penetrate to a certain depth. That's the photic zone. Life can exist in the surface waters. Photosynthetic life, algae, these are the phytoplankton. As they die, they sink to the bottom as marine snow. So there's plenty of things that can also live on the bottom, but they're not getting their energy from photosynthesis. They're getting it strictly from breaking down organic material and so on. So we'll look at those zones, those biological zones, in a minute, but that has a lot to do with the shape of the ocean floor. This is a passive margin. There's no shelf break here. If there is, then you'd see subduction, and you'd get a trench, and you'd get a back arc volcano, that kind of thing. So even though it shows a little bit of that, that's not really what this diagram is showing. I do want to point out, again, tides. Just a little bit about tides. The moon is pulling on the Earth. The oceans are not attached to the ground except by friction. The Earth's own gravity pulling the water towards the core creates friction between the water and the land. Same thing with air in ground or air in oceans. They're not connected by anything other than that force of gravity. So the moon is able to sort of pull the oceans away from the Earth just a little bit. And as the moon goes around, it sort of pulls the oceans in a wave all the way around as it goes. A tide is basically a wave. It's just a big wave that takes place in two peaks every day. The sun is also part of this. It's not just the moon. The sun is also part of this. So you can have some tides where the sun and moon are working together, that you get particularly high tides. If the sun and moon are working opposite of each other, you get intermediate tide. So throughout the year, you can have high tides and low tides that aren't the same. So it's worth mentioning all that. So if you look at the life in the oceans, here's that same sort of continental shelf, slope, abyssal plain kind of diagram. The plankton that live in the surface are phytoplankton and zooplankton. So phytoplankton can produce energy from photosynthesis. Zooplankton then eat the phytoplankton. Larger things eat the zooplankton. Even the whales will eat zooplankton. It includes krill and shrimp and things like that. These things, the phytoplankton typically can't move around much. It just floats in the surface. The zooplankton sometimes can come down and go back up and down and go back up because they want to be up at nighttime, feeding at night, so that things like fish and turtles can't find them as easily. Then they sink down below the photic zone during the day. This diurnal migration is a characteristic of the zooplankton. But there's also plenty of excuse me, what are called nekton rather than plankton. And that includes all of the swimming fish, things that can swim against a current. So even if a current is flowing again, one way. The plankton go with the current. They're not strong enough swimmers to avoid it. The nekton can. Remember Finding Nemo, the turtles get in the current and they get out and, stuff like that. And then there's also stuff living in the benthic zone. The benthic zone might include plants if it's close enough to the surface for light to get to the bottom, but it fairly quickly becomes dark, and so you get types of organisms like, in the deep sea cucumbers, and really weird things. There's some really interesting things down there, including things like the anglerfish that has the bioluminescence on its little lure that it uses to catch. It's what's called an anglerfish because it's like a an angler, or another word for fisher person. I don't want to say fisherman, but I guess that's the term. And a lot of interesting things down there. Lots and lots of stuff. And we're still finding stuff. Really, the deep oceans are less explored than near space. All right, I got to get to the quiz pretty quick. Let's talk about what the major concerns are real quickly. The biggest is going to be the availability of clean water, and this is a particularly global problem because as population rises, the demand for water is increasing, but we're also now using water for more and more things. We use it to frack oil out of oil shale and gas. We use it to, again, not only drink and cook, but wash things, clean things, all kinds of stuff. So the use of water, the demand for water is growing. There are certainly going to be parts of the world where they're going to be starved for clean water, and other parts of the world where there'll be plenty of clean water. We're spoiled at this point by the availability of clean water, but even here it's changing a little bit, so we'll have to keep an eye on some of that. So anyway, again, I'm going to skip through this pretty quick, but where Earth's water is, how it's distributed. We also rely a lot upon the water resources that we have for our food, and ultimately all of the Earth's ecosystems rely upon the oceans, because it's the production in the oceans that then produces the oxygen and everything else that we need around for all living things. Eutrophication is a real problem if you put too many limiting resources into the oceans, that it uses up all the oxygen, it kills all the fish. Those kinds of issues are important. This is a picture of what are called the garbage patches that are starting to form. All of the plastic and trash that we throw out on the ground, it all ends up in the ocean because all streams lead to the ocean. Again, Finding Nemo, all drains lead to the ocean, right? So it's all getting out into the oceans, and the currents are starting to concentrate that trash into specific spots. And you can take boats out there and you can see this just huge amounts of trash out in the middle of the ocean. It doesn't make any sense that it should be there, except that we know we can now watch this process. Matter of fact, I have a little video I think we'll end with. These ducks. This is an interesting story.
In the winter of '92, a Chinese freighter was crossing the Pacific. A storm came up, rocked the boat, causing damage that was quite specific. A shipping container marked for years slid portward with gathering speed. It hit the rail with a great thud, split open and fell into the sea. Oh my God, said the first mates, as the flotsam was beginning to grow. A great armada of rubber ducks was bobbing in the ocean below. They drifted off to the Northeast, on one little line. Don't worry, said the captain, they'll sink, everything will be fine. They'll sink, everything will be fine. 29,000 ducks floating in the ocean. Into Earth's biggest bathtub they did dive. Yellow rubber ducks heading to Alaska. No one ever thought they would survive the ocean tide. 9 months later, a fishing crew was puzzled by what they found. Dozens of yellow rubber ducks swimming in sick of sound. The oldest city in the shore. 80 miles west was the rest of the flock, some 29,000 more. Meyer was in his office when the first phone call came. How the hell did they get here? The oceanographers must explain. He replied, the Aleutian current is driving them with its force. According to my calculations, the rest must be heading north. The rest must be heading north. 29,000 ducks floating in the ocean. Things were as big as bathtub, they did dive. Yellow rubber ducks heading to the Arctic. No one ever thought they would survive the ocean tide. The freezing Arctic waters will make the rubber stiff. Then icebergs will do the dirty work and smash the ducks to bits. Meyer smiled grimly as he announced the ducks sure doom. His colleagues nodded knowingly as they filed from the conference room. The Arctic winds blew bitter as the ducks passed the Bering Strait. Their rubber skins grew brittle as they sailed toward their sad fate. But recent global warming had made the temperature increase, and the iceberg stayed well to the north while the ducks raced to the east. The ducks raced to the east. 29,000 ducks floating in the ocean. Into Earth's biggest bathtub they did dive. Yellow rubber ducks to the North Atlantic. No one ever thought they would survive the ocean tide. Some ducks washed up in Greenland along its glacial shore. Then just 4 months later, a few were spotted off Labrador. And his phone rang daily with sightings and reports. So he called his friend, the climatologist, to ask him for his thoughts. His friend said, I'm sorry, the outlook is quite dire. Solar rays break down rubber with its ultraviolet fire. But the only effect of the sun's rays was to bleach their color light. The fleet continues southward with the U.S. now in sight. The U.S. now in sight. 29,000 ducks floating in the ocean. Into Earth's biggest bathtub they did dive. Yellow rubber ducks heading to New England. No one ever thought they would survive the ocean tide. If you stroll on Cape Cod sands later on this week, and you should spot a yellowish bird with a slightly orange beak. Back off slowly, but please do not delay. Dial the U.S. Navy, the invasion is underway. The invasion is underway. 29,000 ducks floating in the ocean. Into Earth's biggest bathtub they dive. Yellow rubber ducks heading to Washington. No one ever thought they would survive the ocean tide.
True story. All right, we're going to stop there. But that is a true story. And It's an interesting one. All right, let's get to the quiz, though. I know that ran over a little bit. All of our class quizzes are going to be in this same unit. Oh, not 6, 7. No, not 7. Well, I did this one out of sequence, but that's how it was on the syllabus.
What unit is it?
What's that?
7?
8, actually. Let's get to here. See, environmental science and sustainability is in chapter 8. And again, there's a lot of additional information in the book than I can cover in lecture. Also afraid, let's see. Yeah. The tests will come from the book, so we'll talk a little bit more about that as we go. But let's get through this real quickly. Is air a natural resource? Yes, it is. Is Antarctic bottom water crucial for the Gulf Stream? That's what AABW means, Antarctic bottom water. Yes, it is. It's very important. If it wasn't for sinking of water at the Antarctic, we wouldn't have a Gulf Stream. And our oceans would not be nearly as productive as they are. There's nothing you can do to help, right? That's false. There's plenty you can do to help. And as simple as changing a light bulb or making a choice about what car to drive, whatever. Is molybdenum a naturally occurring substance? It is. In fact, you have to have a little bit of it in your diet, or you can get sick. So make sure you get enough molybdenum. Of course, that's not a problem if you eat a balanced diet. But we'll talk more about minerals too. Again, we'll get all the way through this one. But can coastal flooding be prevented using seawalls and jetties? This is a local problem, right? And not completely. It can be somewhat controlled, but it can't be prevented. All right, so let's see how we did.
I didn't get number 1, 2, and 3.
Okay. Number 1 is true. Air is a natural resource. Number 2 is true. Antarctic bottom water is crucial for the Gulf Stream. Number 3 is false. There's plenty you can do to help. 4 is true. Molybdenum is naturally occurring. And 5 is, I said, you would get credit for either true or false in this one, but I said false. It can't prevent flooding. It can control flooding to some extent. All right, sorry to run over 8 minutes. So I'll see some of you in half an hour. I think I can track you whichever one you did. Really, the CRN you should pick is the one that goes with your lab. So it's probably the 12570 or 571. Which lab do you go to?
The Thursday.
Thursday. So that's the 71.
71?
Yeah.
So what was the number, at the beginning when you had picked?
Yeah, I just picked the first one just because we're,
So it don't matter which one that I chose?
You want to pick the one that's connected to your lab. So if you're in Thursday's lab, I think that's the 1257 or 71.
Okay.
Yeah.
Thank you.
But I think I can track you anyway.
Okay, thank you.
All right.
I had 2 quick questions. I tried to do the quiz that we did in class last week, and I did it, and it came out like all zeros. So I think what I did, I didn't press like submit.
Yeah.
At each one.
Okay.
So do you think I could like redo it?
If you can redo it, go and redo it.
I
If
can't.
not,
I try to redo it.
okay, send me an email then telling me what.
Okay. And then whenever you're setting up for, 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 whenever you're setting up.